how do we classify matter? As chemists, we love to sort and put things into groups. That teaches us something about the members of the group, but also teaches us things about the members of that group compared to members of another group. As a result of this video, on the honors level, so to a depth that you've never been expected to do before, you will compare and contrast and give examples of all the different classifications that we're going to go through. I encourage you to create on a piece of paper this general schematic, and we're going to go and fill in these blocks. Now these will be addressed in this video, and then we're going to see we can further break down this classification here, but that will be in a video to come. All right, I'm going to keep referring back to this breakdown kind of schematic, if you will, as we define things. So we already know what matter is. Anything that has mass and takes up space. And we know all the things that we associate with it. It's conserved, it has inertia. Talked about how mass is different from weight and matter is different from energy. So if we would assemble things from around the classroom or from around your desk or things from your backpack, what kind of category would those things fit in? Well, the first most basic breakdown of matter is any sample that you can come up with is either a pure substance or a mixture. Now we need to be very, very careful carrying in the use of everyday adjectives like pure, substance, and mixture into chemistry, because we often in chemistry just define things a little differently. So, what exactly is a pure substance? All right. A pure substance is a sample of matter that cannot be physically separated. So you cannot take that substance and break it into smaller pieces with tweezers or forceps. You can't run it through a filter and separate out the parts. You can't heat and drive away one liquid from another liquid. Okay, that's pure substance. So, a mixture is a sample of matter that can be separated physically. So, for example, your bag of Halloween candy. You can easily pick out your favorite candy bar. You can easily leave behind the things you're not so happy to have. Now, there are certain characteristics of mixtures. So they are two samples of matter that have been physically combined, and they can be physically separated. Another example is sand in water. Now, you know that you can run this through a coffee filter or a paper filter and separate easily the sand from the water. They are physical combinations. They can be physically separated. But also, the components of the mixture retain their original chemical identity. Even though the sand and the water molecules are right next to each other, that doesn't mean they transform and you no longer have sand or you no longer have water. Just like in your bag of Halloween candy, if your favorite candy bar is Twix, well, what if that Twix bar is next to candy that you don't care for? I don't know, a Tootsie Roll. Well, does that mean that because they're next to each other, you're going to get some kind of in-between product of both of these when you go to pull it out? No, the Twix remains the Twix and the Tootsie Roll remains the Tootsie Roll. So the components retain their own properties. The mixture is a result of those individual components. Another example of a mixture is Kool-Aid. You know, to make Kool-Aid, you have the flavoring, you have the coloring packet, you add sugar, of course, to water. The water remains the water and the sugar remains the sugar. The outcome, though, is kind of a benefit of the properties of all of these combining. Okay, so mixtures, 2 or more samples of matter that are physically brought together and can be physically separated, but the components retain their original chemical identity. All right, there are 2 kinds of mixtures, homogeneous and heterogeneous. All right, now, it is not homogeneous. I'll talk about that in a moment. Homogeneous, the prefix homo means the same. Hetero, the prefix hetero means different. So how does this apply to a mixture? Well, homogeneous mixture is the same in its composition throughout the sample. So, for example, the Kool-Aid. Now, if you've made it per the directions, your first sip, your 50th sip, the 100th sip should all be the same. If we looked at it under a microscope, there should be an equal distribution of sugar and flavoring and water, sugar and flavoring and water, sugar and flavoring and water. Where heterogeneous is different in the composition throughout the sample. So, the sand in water. We know if we let it sit, the sand will collect along the water. So if we take a sample from here, it'll have much less sand than if we take a sample from there. Your bag of Halloween candy. It's very unlikely that if you grab a handful from one area and a handful from another area, that they will be identical in their composition. So, if we go back, it doesn't matter which one, but this would be, for example, a homogeneous mixture and then a heterogeneous. All right. Now, how do we tell if something is a mixture? Well, just think about, okay, how was that made? Or could I easily separate it? So, for example, a cup of hot, freshly brewed coffee. That is made by passing hot water through a filter that contains grinds. All that's happening is caffeine and certain tannins and other substances are just dissolving in the water. Now, if I take a sip then from the top, from the middle, from the bottom, and if I looked under a microscope, I bet it would be consistent. But could I separate it physically? Well, if I take that cup of coffee and I gently heat it, I'm going to drive away the water and I'm going to condense. And it's going to get more pungent and more pungent and more pungent in its flavor. So I'm just doing a physical change to separate the water out. I just did a physical change to make it. So if you're trying to figure out if something is a mixture, okay, think about how you made it, or is it easy to separate? Homogeneous, the same throughout. Now, there are some exceptions that may appear as if they are homogeneous. For example, milk. Milk is put through a process called homogenization. That distributes the fat globules. It breaks them up so they can be more easily distributed so they don't rise to the top. Even skim milk. So milk is a heterogeneous mixture. We have to look at it under a microscope. So we are telling you milk is heterogeneous. Even though, unless we talked about it, we'd probably categorize it as being homogeneous. So in my cup of coffee, if I add creamer, whoa, that changes it from homogeneous to heterogeneous. Let's see. Homogeneous mixtures are also known as, right? That's AKA solutions. So that's something to make a note of. Okay, so that's what we want to talk about as far as mixtures are concerned. So now, pure substances. Pure substances cannot be physically separated. All right, so what are they? Pure substances are either elements or compounds. Elements or compounds. All right, so some more definitions. An element or a compound cannot be separated physically. So we have this gorgeous periodic table. Here is a listing of our elements. So how do you know if something is an element? Well, you can check the periodic table. In honors chemistry, you will never have to memorize the periodic table. It will always be a resource for you, but we will be using it daily to come. And so you'll just, out of just habit and use, get to know where everything is. So again, we never have to memorize this. We just have to know how to use this amazing tool. Okay, so how do elements differ from compounds? Well, an element is a specific type of atom. All right, well, what's an atom? An atom is the building block of matter, the most basic building block of matter. Now, we will, in Chapter 3, begin to talk deeper and more, definitely more about atoms. Okay, an atom is made of protons and neutrons surrounded by electrons. That's all we're going to say so far. Now, that is really generic, just to say atom. So, to use the word atom, that's something similar like using the word student. You are all students. Well, there's a whole bunch of different atoms, just like there's a whole bunch of different students. So a specific atom is oxygen. What makes oxygen oxygen is the number of protons in its nuclei. So that's what makes oxygen oxygen. Hydrogen is a different atom because it has a different number of protons in its nuclei. Well, just like we can have students, well, we can also have Sarah Gerhardt. That is a specific type of student. And we can have Abram Gerhardt. That's a specific type of student. Okay? So just atoms are generic, but a specific type of atom, and the type is defined by the number of protons, well, that gives us individual elements. Just like student is generic, but your name, you are an individual. Okay. If we put protons together, we don't get anything. If we put a bunch of electrons together, we don't get anything. But if we put atoms together, that's how we get matter. So, the most fundamental building block of what our amazing universe is made out of, as far as matter, those are atoms. But if we look at the atom and look at the number of protons in the nuclei, well, that determines what element it is. Okay. Elements cannot be broken down physically or chemically. So you can't separate the protons, neutrons, electrons with tweezers or by putting it through a chemical reaction. Okay, so that's what makes an element an element. A compound. Compounds are made of two or more elements chemically combined. So they can be chemically separated by a chemical reaction. Also, whenever you combine elements, now, of course, you can make a compound by reacting two or more elements. You can also make a compound by reacting an element with a compound or two smaller compounds. But your compound has totally new properties and a new identity than the individual elements that made it up. So that is what distinguishes a compound from a mixture. Remember, a mixture is two or more substances that come together and they retain their own chemical identity. Not so with elements combining. And a great example of that is reacting sodium with chlorine. Sodium as an element is one of our most reactive metals. It's an alkaline earth metal. It is silver. It is very soft. You can cut it with a butter knife. It is explosive in water. Chlorine is a yellow gas. It is poisonous in very small quantities. If you react these two together, we create sodium chloride. An ionic compound, white, solid at room temperature pressure, soluble in water, not explosive in water, and this delivers, of course, the sodium ion and the chloride ion, but the sodium ion that enables our nerves to communicate to one another. So we could never ingest pure elemental sodium, pure elemental chlorine. This would harm us greatly. This would consume our lives. But look, they react, and when they combine, they produce something with a totally new chemical identity. Oh, isn't chemistry just wonderful? Okay, so that gives a basic overview of the classification of matter. We will talk about the further breakdown of different elements to come. What you need to be able to do is give examples of each of these. And if you're given an example, could you classify what it is? And can you, from the honors perspective, compare and contrast these? And we start with really understanding what makes pure substances different from mixtures. Then, okay, is the composition consistent or not? And then, okay, can I find an element on the periodic table, or can I not separate it chemically? And then moving on to compounds, can I separate it physically? And if not, then of course it's a compound if I can only separate it into elements chemically. Do not worry, we will show you, okay, what do you have to know with this information? We recognize you're just beginning your chemistry journey. So the practice that we're going to do will show you how we expect you to apply this information.